They have right here. The vote on.
So originality, so API statement.
Yeah. That's different. Yeah. Yeah, where did we?
All right, we are going to go ahead and get started. Could everybody raise their hand if you can hear me? Okay, so that's pretty good. If you didn't raise your hand, although I can tell that you're not really paying attention, if you didn't raise your hand, you need your earpiece radio on. Okay, there we go. Great. All right, we're going to go ahead and get started. Hello, everyone, and welcome to the 2026 SIIM Hackathon Showcase. I will tell you that this is my favorite event of my favorite show of every year, and so I'm very happy to be here. My name is Teri Sippel, and I'm at the Johns Hopkins School of Medicine as well as Marquette University, and I'm going to be your moderator today. I've been involved in the SIIM Hackathon. Okay, they want me to tell you how many years. I refuse to do that. This is the 13th SIIM Hackathon, and we have 10 fantastic teams that are going to present. I'd like to say thank you to all of the participants. This year we had a record number of projects, and we did something a little bit differently this year. We did a preliminary round of selection, but we really want to thank everyone who was present and who did some of the development and just came up with ideas, because we're grateful for that, and we value all of our participants. I'd like to thank our code heroes and our domain experts who helped out with the different teams this all week long. I would like to thank the judges from the preliminary round for dedicating their time to leading up to this meeting, and that includes Wyatt Tullis, Tom O'Sullivan, Kevin O'Donnell, Sahika Batul Ayeli, and Steve Horry. And then I would like to thank our judges who are sitting up here, our esteemed judges who are sitting up here in the front row, and that includes Howard Chen, Wyatt Tullis, Mark Coley, Sylvia Devlin, and Kevin O'Donnell. So thank you all for your time. Okay, I think they're trying to suck up to you guys. But anyway, finally, I'd like to give a huge shout out and thank you to the SIIM Fund, especially the individual members and the corporate members. It is through the philanthropic efforts of the SIIM Fund that we were able to provide 5 different scholarships for the hackathon recipients, as well as 2 for the NICRAD. And they support the travel awards for some of the students who come to the hackathon. Specifically, I would like to call out the corporate sponsors. We have the corporate partners of Fujifilm, Double Black Imaging, Radical Imaging, RAD.AI, Pocket Health, Visage Imaging, and Mach 7. We have the corporate friends of Siemens Healthcare, Health Data Movers, and Doc Panel. So we're really grateful to our sponsors, because that's how we're going to continue this and involve more and more young people as we go forward and kind of pay it forward. As a reminder, when everyone's complete, please don't run away. Please take some time and go through and select the Audience Choice Award. So that's the final award. There'll be 3 different participants, 1 through 3 awards, and then there's the Audience Choice Award. The Audience Choice Award comes from you, so we'd like a quorum to vote. And if you're on a different team, you can vote for whichever team you would like to vote for. So team members can also vote. Each presentation will have a total of 7 minutes, with 3 minutes, really 2 minutes for Q&A. So if you go over, I'm going to give you a little bit of a here. Okay, first of all, here's the SIIM Fund sign. I forgot to show you the chicken. If you go over at 5 minutes, I'm going to show you the 5-minute warning sign is the chicken. At 7 minutes, I will do a soft boot off of the stage. So if you look like you're wrapping up, that'll all be fine. But at a little bit after 7 minutes, you're going to get a hard boot off of the stage so that we can get some Q&A from the judges. So, any questions, teams? If you are having issues with the Wi-Fi, we recommend that you go to the Hackathon network. And the password for the Hackathon network is Bridges, all uppercase, BRIDGES 26. On that note, I would like to bring up the first team, which is Cleanup in Bay 5.
All right. Hello, everybody. This is our SIIM Hackathon 2026 project, Cleanup in Bay 5, also known as Cub 5. We are standardizing clinical imaging data via automated DICOM header verification and cleanup. My name is Abby. Up here, I have my teammates, Will and Delaney. So our clinical use case is actually based off of actual situations that some hospitals in Colombia are currently facing. We have our patient Maria, who is a 58-year-old woman. She visited the hospital because she woke up experiencing chest pain. Her physician was concerned and orders a CT of the chest with no contrast, where Maria's images are taken on a CT scanner from Standards Optional Incorporated. Although both Maria and the radiologist technician believe that everything seemed to go well with the scan, there was a lot of internal issues occurring due to outdated technology being used. The scanner attempts to send the study into the PACS, but Standards Operational Incorporated input letters into the study instance UID, which should just be numbers, and use an improper format for acquisition time. As a result, PACS rejects the entire study. The on-call thoracic radiologist, Dr. Chen, waits completely unaware of what is happening, as does Maria, who is currently sitting in the waiting room, feeling quite nervous and eager to get her results. After hours of waiting, hospital IT is finally contacted. They have to access the images through the local network and manually change the UID, pushing it into the work list. Unfortunately, the acquisition time error goes completely unnoticed. But the issues don't stop there, because although the study is able to arrive in the work list, there is a lot of issues with the DICOM header, such as the body part examined is marked as brain when it should be marked as chest. It has a very poorly written series description and incorrect procedure code sequence. Patient demographics are also missing as well. As a result, the routing algorithm ends up reading brain instead of chest because chest is not present in that area, and connects the study to Dr. Patel and neuroradiology, prolonging Dr. Chen's and Maria's waiting and delaying workflow. IT once again has to be contacted, who routes the image manually to Dr. Chen's workspace. After making a special change request, IT updates the body part examined to chest in unstandardized code. Unfortunately, once again, a lot of these other parts of the DICOM header, such as the procedure code sequence, patient demographics, everything like that, goes unchanged and uncorrected. So the problem that we're dealing with here is that the direct transmission of studies from modality to PACS causes inconsistent and non-standardized DICOM metadata, disrupting workflow and downstream AI processing. The lack of monitoring causes issues including delayed radiologist interpretation, misrouted studies, reduced interoperability, and an increased risk of loss of images.
So our goal is to prevent this by creating an application that sits between the modality and the PAC system so that the DICOM headers can be cleaned prior to that storage. So here's just a little workflow of what that looks like. As you can see, we have the modality on one side. Then as the DICOM image comes through, it will go through our program, Cub5, but prior to being sent to the PACS. This ensures that the radiologist will be able to efficiently get a clean DICOM header with all the information they need. We'll go into a little more detail on that later, but first we're going to just show a quick demo of what the UI will look like for that. So our UI is run on a Django server, which you can see is getting started up here and opened. So this would be for a IT at a hospital so that they are able to track what changes are happening in the various DICOM images and then also filter the information as the IT knows the main problems that are happening in the hospital, we want them to be able to track what changes are being made to see which problems are most prevalent. So here we are just sending some DICOM objects through, and as you can see, our server is currently listening for those right now. So then once those are sent, it has a log that lets you know when they're received, and then they are immediately processed, which you can see on the bar on the side there. You can also stop this processing if adjustments need to be made, and then things will wait in that queue until it is ready to start again, and then it will immediately process. So then here's just a quick example of Maria's study and what it would look like to the IT to see what all the adjustments that were made. As you can see, there were some daytime formatting errors which were fixed along with the UID. Some demographic information was messed up, such as her age and name, which were then fetched from her EHR to be adjusted. And you can see all the things that were changed there. Additionally, if the radiologist or if the IT wants to look at specific modalities on the side, they can change which DICOM images they're looking at to filter that information. And then on the other side, they are able to filter what actual DICOM header information that they're looking for being changed. So in our current implementation, what we have right now is for format, the UID and daytime format adjustments. For standardization, you can look at the body part examined, series description, and procedure code. And then for our completeness check, we have our demographic data right now. And then for the final part of this UI, the IT can also filter out these logs based on whether or not they want to see what's going on the server, or just generally look at which DICOM objects are currently present.
Moving forward, we just want to resurface after the demo on our workflow. So we had the addition of our standards and APIs used throughout the system. So first being LOINC, which ended up fixing the procedure codes through mapping corresponding to provide those codes going forward for a standardized format. Then we used for the anatomical region sequence, we used Total Segmentator, which went through and mapped the SNOMED codes in the images. And then lastly, we used FHIR API queries that queried the EHR and then mapped those codes to verify the proper data was being sent. Then we just, as I previously mentioned, we have the standards and APIs used, which is FHIR, DICOM, LOINC, and SNOMED. And we would also like to disclose that we use generative AI throughout this process to help with the implementation of our code. So through this project, we summarized three main problems. First being correcting and validating the format of this data, standardizing unformatted data, and then checking for those completeness of the data reports. And through this, all of these correct manufacturing errors in these DICOM headers going forward to improve the lives and day-to-day errors that these radiologists and ITs go through to also improve patient care as well. And then lastly, we would just like to thank everyone that helped us throughout this project. We are so thankful for everyone in the SIIM community as well. So if you have any questions, now's the time. Thank you.
So one question for you. What fantastic project, fantastic presentation. Thank you so much. What was the source of truth that you used to identify the LOINC code? Because the procedure description was wrong. So how did you know what was right?
Yes. So online we downloaded the LOINC mapping tables, and then we used some Python libraries to end up parsing through the Python tables and the code itself that was in the DICOM header. And then we used word matching to end up comparing the values. And then we gave the most truthful or most confident code that we matched with.
Yeah, so the input to that mapping process was the study description, or
the free text in the procedure code header.
Okay,
thank you. Yes.
Second question, I love the use of the segmenter to kind of get what the right answer is for the anatomy. When you're messing with, higher up? Okay, now it sounds really loud. When you're fixing the UIDs, so that'll update the identification of the object. Did you also take a look in the other objects where they reference to that UID? Like, for example, if you had, presentation states or things that were pointing back to it, those would also need to be kind of updated and synced. Any thought along those lines?
No, sorry. We did not have time to go through and reorient all that data. Yes.
Fair enough.
one more question around the reversibility of the edits. So whenever you make changes to the headers, there's a possibility that it could be incorrect, that could be caught by a downstream audit. What levels of reverse? I saw a log, but to what extent can those changes be reversed easily?
Yeah, as of right now, we don't have that in the implementation, but throughout the hackathon, we end up talking with some other groups, and that got brought up as something definitely that should be implemented in the future, that the IT tech has the ability to reverse changes or re-edit them manually after the system goes through it. Yes.
Yeah. And actually, if you do start looking at that, the original attribute sequence in the DICOM header lets you store what things were before you messed with them. So it's essentially a built-in log. So
Perfect. Thank you again.
Thank you. Great job. Next up, we have DIPPS, also known as DICOM PS, which I think is going to become clear to us in just 1 minute.
We don't seem to be able to share. Oh, there we go. Thank you. Good. Run again. That's fine. Am I good to start? Yeah. Okay. Yeah. Oh, one slide behind.
Esteemed hackathon judges and audience, it is my deepest pleasure to introduce you to my very good friend, Bob. Bob is 34 years old. He's a software engineer. He loves the beach. He loves trying new things. And quite frankly, he's not the best decision maker. Now, Bob has been saving up for 2 years to go on his dream vacation. And where's Bob going?
Well, Bob's going to Australia.
Bob is going to Australia, and Bob is very excited. He's even working on his Australian accent. Crikey, mate, the name's Bob. Very proud of you, Bob. I could see you're working very, very hard, and you're super excited. In fact, Bob has packed sunscreen, his flip-flops, and because Bob is actually a responsible adult, Bob has had his international patient summary uploaded on his phone. Good job, Bob. We're proud of you. Now, it's day 3 of the trip. The sun is shining, the waves are perfect, and Bob rents a surfboard.
But Bob has never surfed before.
Indeed, he hasn't, but Bob does not let this stop him. He paddles out, catches his first wave, and for approximately 2.43 seconds, Bob is the coolest sock on the beach.
And then?
And then Bob meets the ocean floor. Bob has a broken leg.
Not Bob.
Bob is rushed to the emergency room in Sydney. The doctors are great. They're experienced, they're professional, and they immediately pull up Bob's international patient summary. The doctors know exactly what medications Bob is on. They know his allergies, they know his blood type. The IPS is working flawlessly.
This is great, but wait. The X-ray is showing something unusual about this leg. The bone structure around the fraction looks off, like it's been broken before and healed in a slightly different position. Has this leg been broken before?
I don't know. Let's ask Bob. Bob, has it been broken before? I don't think he can answer. Maybe he's unconscious, or maybe it's because he's just a sock. Who knows?
Well, is there anyone we can call?
No, it's 3 a.m. Bob's family's in Canada, and even if we reach them, they don't have his imaging, his x-rays, his old scans. They're sitting in a hospital database back home.
So we don't know how this leg was originally set. We don't know the baseline. We're going in blind.
That's right. The doctors, they'll do their best, but without the previous imaging, they can't be sure they're setting Bob's leg correctly. Bob may never surf again.
Wait,
What?
didn't Bob have something else on his phone?
He did.
Because Bob didn't just bring his IPS.
Oh, no, he didn't.
Bob brought his DIPS.
DIPS, DICOM International Patient Summary. Everything in the IPS plus Bob's actual medical images, his x-rays, his MRI, his full imaging history, all of it encoded in a single QR code.
So the doctor just
Scans the code,
and gets?
Bob's complete imaging history, right there in the browser. No app, no login, no waiting for a fax from some random Canadian hospital at 3 a.m. The doctors can now see that, yes, Bob broke his legs 4 years ago. They can see exactly how it healed. They know what they're working with, and they set the bone correctly.
Bob makes a full recovery.
And he flies home 3 weeks later.
Does Bob go surfing again?
Bob does go surfing again.
Well, we tried.
In all seriousness, what happened to Bob happens to real patients every day. 1 billion international trips are taken every year. Medical emergencies are a real risk. And imaging data, the most detailed, most diagnostic information a doctor can have, is almost never portable.
IPS was a great first step, but DIPS is the next one.
Because your doctor shouldn't have to make a guess, and neither should Bob. Now, before we get into the details of Bob's favorite, exciting new technology, DIPS, let's quickly go over the old one. International Patient Summary, or IPS, is an international HL7 standard that provides a concise and complete snapshot of your medical history in event of a medical emergency while traveling. And Epic went live with it about a year ago. Without IPS, ER doctors abroad would have to treat you like a completely unknown patient. So this could cause them to miss critical allergies, repeat scans, prescribe conflicting medications, etc.
Problem. International Patient Summary, IPS, is FHIR only and does not support DICOM. Therefore, there are no images. But we all know a picture is worth 1,000 words. So we decided to make our goal for the hackathon to be adding images into IPS. Some things are just better seen on images, and they can give doctors a better understanding. This also helps in avoiding duplicate imaging, unnecessary radiation, and cost. Our solution is to encode key images in raw DICOM format and embed them into exported FHIR IPS bundle. We also built a web application that provides easy GUI to manage the process, including downloading the export as a JSON file and the QR codes easily shared between devices.
Now we have a quick demonstration. So you can see the website here. There's a Dropbox to select your patient. So we'll go with Neela SIIM for this example. And now we can generate the summary. And there you go. You can see we have the QR code so you can scan and open on any device. And we can also generate the full report. So you can see here patient information, the condition, any allergies or medication, and all the diagnostic reports. Now, this is fairly basic. This is what's already existing on IPS. But then where it really gets special is down here where you can see the DICOM images. And we are improving the technology so it's more specific in selecting only the necessary images. And then you can see here the code. I'll let my dad take it away.
So as you may have seen on the web interface, there's an option to download that FHIR bundle. So that's the magical IPS bundle. Except that in this case, this bundle is now enriched with DICOM images. So again, not the entire study, just key images that are actually very useful. And yes, this is available on the web, so you can scan it with your phones. I will show you the JSON super quick here. So you'll notice it's a FHIR of type bundle, and then you'll see under the hood, we actually have binary resources that contain the images right here. And with that, we will wrap. So put up the wrap slide. We'll take any questions.
Can you hear me?
Yeah.
Oh, great and entertaining presentation. Thank you. So I was just wondering, are there any concerns with, like, it looks like you guys are base 64 encoding the raw DICOM files into the FHIR bundle. Are there any concerns about file size? Because if you put in a really big study, that's going to like increase the size of the files by like 33%.
Yeah, absolutely. So that's the reason why, in an ideal world, these would be key images, and you can go about this two different ways. So you could look at the DICOM studies, look at any key image objects, and then decide to bring these in. Or the more modern, cool FHIR way is you look at the imaging selection, which is a way that you link to interactive multimedia reports, and then you can find these important images, bring them into the record. The reality is these images, if you just take individual ones, are usually very small. So like instead of the record being 100 kilobytes, it may end up being a couple of megabytes, but still, like, it's not that big.
So so you guys are just have you considered just doing like JPEG embedding, like so you don't have to include the entire DICOM file?
That's a good point. So we actually thought about that, but we decided the DICOM file is generally better just because, as you know, these images are 12, 16 bits, they contain window levels, etc. So, you know, the idea is if we can have the other side be able to import them and like put them in an actual DICOM viewer, then someone who's clinical can actually get full value of these images.
What's the solution if the radiologist was either lazy and didn't identify key objects, or let's say that they're using a viewer that doesn't actually allow the creation of key objects or the FHIR resource for the image selection?
Yeah, so for the first one, unfortunately, not much we could do. For the second one, if they're using a viewer that does not support this, that viewer should be reported to DICOM police.
And one word. For the you've got the images in the DICOM bundle or in the JSON bundle. And so where does the rendering happen? And second question would be if they wanted to do an export, so you've got this on your phone, I think you were saying, how does that then get into, for example, a local PACS, perhaps, hypothetically?
Good question. So that wasn't in scope for us. We didn't have time to do it, but that definitely is something that could be doable. So right now, IPS is definitely consumable by an EMR because it's just a FHIR bundle. So in this case, that EMR would probably just have the added step of, oh, look, there's some binary content. Oh, well, it's DICOM. Let me send this to a PAC system, or maybe even like have an inline viewer or something along those lines. We didn't get the chance to do it, but it's definitely possible. Yeah. Thank you very much.
Okay, I'm pretty sure that's the first time we've ever had a SOC at a hackathon before, but it was a very effective SOC. Okay, and next up we have team scan to sign.
Okay, so we're a group from Jacobian, Fovea, and Rayscape. And we took on the task of taking lung cancer screening since we have high volume measurements, detailed data coming in from a CT. This puts a high load on the radiologist to note all of these all the nodules, sizes, rates, so on. You know, we have a lot of movement now with AI vendors that can really well find these, notate them, send them, but we end up with data in multiple systems. We end up with difficult traceability from the PACS to the radiologist to the report. So we took was to use our ambient solution to format these format these findings and put them cleanly into a report. This will help us close the loop. It also provides the radiologist with almost an immediately completed report to sign. So the user story, the radiologist sits down, they open up a lung cancer screening. they would normally validate each, or they would, instead of reading each nodule, they would go into Fovea's cockpit, flip through the nodules RAYScape found, accept, reject, or modify those in each of the states. Those automatically make it into the report. Then the radiologist can just simply sign the report, dictate incidentals, that sort of thing. So we're going to do a quick demo. So we have a standard, we have FFI opened up with our ambient viewer. We can see our nodules from RAYScape have already loaded. We can dictate a little bit of information here, submit it. We get our study information, and then the radiologist can just hopefully pop over to the viewer, but network being what it is. Just 1 second. I knew this. Sorry, folks. Slow network, I suppose. Well, the idea would be, when we first came in, you saw the list of nodules. The nodules should correlate to images here. We can flip through them. We can voice navigate them, accept and reject, and modify right here in the Fovea cockpit. So here you see I remove this nodule. My report, my list of nodules immediately updates. Add it back. We have almost immediate refresh of the report with the new data. Additionally, we have our assist. So we say, we want to double check the AI. Our assist shows this should be a lung RADS 3. However, it's only being reported by the AI as a 2. I can look through my nodules, find the nodule that isn't a 2, modify this. And we immediately update our report to reflect that we're now a lung RADS 3. And now we essentially have our full report with our generated nodules list ready to go. So to do this, we use DICOM segmentation, DICOM measurement transfer, HL7CDA as the backing structure for the report. Obviously, the lung RAD standard for scoring. IHERA, in that we're doing real-time updates. I will say we are not using Firecast for this mechanism right now. We also used open telemetry with the Gen AI plugin to get full traceability through the AI in the background. We did heavily vibe code this. I think 60% of the code is vibe code written. Have contact information. So questions?
So thank you very much for the presentation. It's really fascinating to see, not only people who are kind of entering this space, but people who have been in the space for a while working together to create something, because I think that integration between multiple different vendors is something that's always been a big challenge for our field. So I commend you and your team for doing that. One of the questions that I had about that was this an existing set of relationships that you had, or was this something that you formed like as a part of the hackathon and brainstorm the idea together about how to have the impact?
So we reached out to a few partners that we have worked with in the past through the IAIP, RSNA, and the IHE to see who would be interested in trying to put something together for this a few weeks ago, and these were the people who accepted.
That's awesome. So I think that that's another impact of the imaging AI in practice work that RSNA has done, is really like helping to create these forums for collaboration. So that's awesome. Thank you.
Thank you.
Was there a button embedded in the application, or was the button to get to the different criteria external? Would the radiologist would it be readily available for the reader?
To view the AI cockpit?
Yes.
In this case, there was a button. We also typically would do a voice command.
Oh, that's right. Okay.
In our full implementation, this is, doesn't have quite all the bells and whistles yet.
Okay, thank you for the clarification.
Clinically speaking, there are often two additional nuances to nodule tracking. So one of them would be what happens when there are so many of them, and be having to choose the best ones, and that's usually a radiologist's task. How do you guys handle that? And the second would be lung cancer screening is about how nodules evolve over time compared to prior studies, and how does scan to sign handle those situations?
So at the moment, we had hoped to pull in priors to be able to do prior comparison. That didn't have time to complete that with this iteration, but that would be a future possibility. As far as selecting the nodules to show, RayScape's feature uses the top, it selects the top 5 by size from the current method. I mean, if you noticed, I think there were 22 or so, or 12 in the case we showed.
Thank you. You mentioned that you weren't using Firecast for the kind of desktop integration. How are the applications kind of syncing up?
So in that case, we're not using Firecast. So there's simply parameters that are passed through REST from one to the other one. Essentially, the ID of a study, which is in the message, and it is useful for linking the information here. But eventually, obviously, we come through Firecast. We put a hub in between them.
So just a follow-on question to Wyatt's question. Was it just the complexity of the subscription model that led you to avoid Firecast, or was there something about the FHIR resources that are available to be exchanged that was a limitation?
No, it's not about complexity. It was just about focus. We were trying to show the part where we submit, we get all those nodules, and have the AI interpret them and update on the fly and on those things. So we focused on that. The Firecast piece it's clear enough, and we'll do it for the next RSNA probably, but we didn't see that as a challenge. So. Thank you.
Thank you, Team ScanDesign. And next up, we have possibly the cutest team member. And Brad, I'm sorry, but I'm not talking about you.
That's awesome. Pretty good. Cool. Thanks so much. Here in 1 second, we get set up. Right. Testing. Okay, perfect. I keep hearing the radio. Do you guys hear music? No, okay. I don't know what's going on. It's me. I'm gonna turn off. I can take off my list for a minute. All right. And then share my screen. Perfect. All right, great. Can you guys hear me okay? Awesome. Thank you very much, everybody. My name is Brad Generu, and I am here with my project, RADReachy. Let me just power up my robot here, friend. Getting a little warm. We don't need his hat on. So we'll just start him up. 1 second. Oh, cool. Thank you. My matching hat. I won't put it on though. Sorry, hang on. So while I wait for that to come up, here he comes. All right. So what I wanted to do is something a little bit different, which is looking at how do we create a radiology registration concierge extraordinaire. This is RADReachy. This is an open source robot project that Hugging Face and others have put together. Oh yeah, there's my disclosures. I wanted to tackle how do we actually streamline the registration process. Not only, oh wow, it's really laggy. Not only is it from a in-person registration, but also building the entire brand from being able to take phone calls, being able to have an online chat bot. But I wanted to show a physical manifestation of what this looks like. Looking at, how do we address staffing pressures? How do we address handling all of the patient's questions? Things like around collecting demographic information, insurance information, prior authorization, covering the safety screening. Are you pregnant? Do you have any metal bolts in you? And look at how do we account for all those potential downstream costs. So, Rishi, are you there? Let's see if he's on. Oh, I didn't hit. Here he comes. Hey, Rishi, are you there?
Yep, I'm here and listening.
Yeah.
My circuits remain modestly attentive.
All right, great. So RADReachy open source bot, completely fully open source using Apache 2 license, using the ROS2 robot operating language, using language and speech models, also all open source, using Python. Everything is customizable. I can run on premise, I can run in the cloud, I can run in hybrid, whatever makes the most sense. Because it's fully customizable, I can connect to EMRs, I can connect to PACS, I could use DICOM and FHIR standards. All these things I can put together and connect this with the face of my robot here. So rather than go through my slides, let's see if I could actually just do a demo. So let me just grab my prompts. In the interest of time, I'm going to do this myself.
Oh, got it. You take the controls and I'll stay quiet unless you want back.
He's very chat. And so hang on one sec. All right, so. Hey, RADReachy, are you there?
I'm here and close. It's RADReachy, not BradReachy. Easy mix-up. I sound very registration desk chic.
Hey, RADReachy, I'm here for my scan.
Welcome in. First, may I have your full name?
Yeah, it's Brad Generu.
Thanks, Brad Generu. What's your date of birth?
January 1st, 1970.
Got it. January 1st, 1970. What are you coming in for today?
I'm coming in for an MRI on my back.
Thanks. An MRI for your back? Do you have any metallic surgical implants?
No, I don't.
Thanks. No metallic surgical implants noted. Do you have any questions for me before I notify radiology?
I'm a little bit claustrophobic. A little worried about this MRI. Am I going to be okay?
Most people do okay, and the MRI team can help with claustrophobia, but I can't give medical advice. Would you like me to note that concern for them?
Yeah, that'd be great. And I have no more questions.
Thanks. I'll note that you're concerned about claustrophobia and notify the radiology team you've arrived. And I'll send a FHIR message to the radiology PACS system.
Because of course the patient wants to know that they got FHIR messages to the PACS. Fully multilingual. I could do things like bonjour RADReachy, comment ça va?
Yes. If you ask me in French, I can reply.
My French is terrible, so, but I did earlier a full workflow of doing a patient registration in French, en français, and he did great, except for he kept telling me he couldn't understand me en français. So anyway, all right, I'm going to shut him down and just walk through the last couple of slides. Thanks, RADReachy. Say bye to everybody.
Goodbye, everybody, and thanks for visiting. I'll leave the dramatic exits to the MRI machine.
All right, cool. All right, so let me shut this down. And all right. So as I said, so really quickly, in the last like 1 or 2 minutes, did a registration workflow covering off, questionnaires and things. All of this is customizable. I can connect into things like EMRs, the RIS, with FHIR, with HL7, all these things I could build myself. The benefits are oh, jeez. Short, things like streamlined onboarding of the patient when they come to the hospital, working through a unified experience for the patient, being able to answer questions whenever the patient actually has them. What I've done is I've built this on the RADReachy platform. I had a lot of problems getting access to the internet with the Wi-Fi, so I have a hotspot. I had to run out to Best Buy on Wednesday night. So I spent a little bit too much time trying to get it to go here. I would have liked to actually do FHIR, actually stand up a RIS, actually connect to these things. I plan to bring my own LLM server. I couldn't fit it in my luggage, so I didn't bring that. So I'm doing this in the cloud. I could do, much more like connecting, doing, what else should I look at from a safety screening logic? And then I'd ultimately doing some kind of measurement impact of, is this something that's useful, that's helpful? So with that, I'm happy to take any questions from the judges. Let me put my headset back on. Thank you so much.
Hey, Brad. This is very interesting. Thank you for putting together this demo. I really enjoyed it. My question is around in the future state or in the ideal state when you use a local LLM, my question would have been around the knowledge base and how do you handle disambiguation? So in the demonstration, we heard at least two different situations. One would be disambiguating the spelling of a name. So depending on the pronunciation and things like that, the system would have to kind of identify who the actual patient is accurately. And the second piece is around kind of MRI of the back, which could mean a number of different things. And the system would have to identify what is the proper exam being referred to. How do you handle the knowledge base part of the problem?
So the technology is continuing to evolve. So I can plug in the large language models that I've built or that I've customized for myself. I can connect with OpenAI, with Claude, with anyone that, basically that I can connect into. I can customize them. I can load in my own languages. Even on the speech side, again, I'm using open source speech libraries. They're getting better and better. They can cover things like speaker diarization. So for example, imagine the patient comes in with their mother or a translator or a social worker, being able to handle when you've got multiple speakers and knowing who is who as part of that conversation. Adding in things like guardrails. One of the things that I've looked at in the past is what if you talk to the RADReachy bot and say, hey, I saw my neighbor in the waiting room. What is he in for? You need to be able to do all of those guardrails to protect those conversations as well. So over time, I mean, we can account for all these things with prompting or with customization on top of that. But it's actually a factor, not so much of the bot, but actually the underlying LLM.
And have you thought about sort of some of the associated paperwork? You know, it's like, have you signed your HIPAA form? And oh, I brought in this paper from my referring physician. And
I've thought about it. I mean, because it can be customized individually to the institution, accounting for those things shouldn't be too hard. Because I can talk to him and say things like he asked me if I had any questions. If I were to say, hey, I brought a form with me and I want to give that to to the registration desk, he should be able to pick that up and do a tool call to send a message somehow for that. I think that we would run it pilots in hospitals and look for those kinds of, I think 90% will be specialized to be able to account for that and really human in the loop hand holding as we kind of, use this to help augment what we're doing. Hi, I'm done. I couldn't see your chicken hat, my chicken hat. So great. Thank you so much, everybody. Sorry.
Okay, what was going through my head was I never should let Brad and Kevin talk to each other. Anyway, moving right on. This is a SIIM hackathon of first. First we had a sock and now we have a robot. And now we have VerEIT.AI, which is our first online team. I'm not quite sure how I'm going to give you the 5-minute sign. I'll try tapping on the microphone, I think. Go ahead.
Tamara or Leonardo, you're up now.
Wait a minute.
You can go ahead and share. Do you need another minute? We can move on to the next and come back to you.
That might be good, thanks, sir. I don't think Leo's quite ready. Oh, there we go.
Right, you're up.
Can you see? Can you hear my voice? That's okay. Can you see my screen and hear my voice?
Yep, looks great. We can hear you and see you. Thank you.
Okay. Okay. Good morning, judges, mentors, and fellow innovators. I'm Leonardo, representing the VerEIT.AI team. Where we are, I want to introduce about our project that's physics, law, and medical domain guided AI to enhance spatial resolution of electrical impedance tomography or AIT for low cost, safe, and portable lung cancer detection and monitoring system. Okay, and look at the reality that lung cancer is the number one cause of cancer related death globally. It results in nearly 45.6 million per year healthy life years lost, and also costs around more than 200 billions US dollar per year. And so, but in Indonesia alone, it affects over 34,000 people. Currently, monitoring relies heavily on CT scans. However, repeated CT scans expose patients to cumulative ionizing radiation, increasing secondary malignancy risks. Furthermore, CT infrastructure is extremely costly and highly inaccessible in remote archipelago settings. To validate this, we conducted primary research through expert interviews with oncology and internal medicine specialists confirming a critical need for a safer, portable alternative. And then our solution is VerEIT.AI. If you look at our decision tree, AIT is the only modality that is highly accessible, portable, and poses zero radiation risk, and operates at a low cost. The historical issue with the AIT has always been low resolution, low spatial resolution, and that is exactly what our AI fixes. And this is the clinical workflow that operate from the phase 0 until the phase 3, where we perform preliminary screening using portable AIT devices in rural clinics. And then if a patient is referred to a major hospital, we extract a 3D anatomical mesh from a standard baseline CT scan. And then this is our core engine. We use physics assemble AI that combines the patient anatomy mesh with Maxwell arithmetic equation to accurately reconstruct the lung conductivity map. And then for the phase 3, we do a real-time monitoring. And this is the diagram of the API where our app works. And then this is the result and discussion of the of our research. You can see we recently evaluated our AI against conventional methods. Globally, our deep learning ensemble significantly outperformed the classical Jacobian inverse method. We achieved a lower mean absolute error and root mean square error, and while pushing our structural similarity index to 0.669. And then when breaking this down per class over tumor, pneumonia, and pleural effusion, the excellence of our model becomes clear. As you can see on the screen, our AI reconstruction are visually much closer to the ground truth, and the error map demonstrates that our deep learning approach drastically reduces the views and artifacts and provides precise localization of abnormal region. It is important to note that VerEIT is designed to complement CT, not to replace it entirely. CT provides the initial baseline, while VerEIT takes over safe, frequent monitoring. And then for the innovation and novelty, when compared to existing imaging modalities like PIT scans or standard AIT devices, VerEIT stands in a class of its own, and our method is 40% faster than conventional AIT inversion. By utilizing this technology, hospitals can reduce CT scan usage for monitoring by up to 80%, and while unlocking massive cost saving of approximately 37.5% per patient. And look at the market opportunity. There are total addressable market units is at $21 million annually. And beyond the financial metric, this system moderate national imaging costs, optimizes radiology capacity, and most importantly, save patients from harmful cumulative radiation. And this is the demo one, the video you can see. This is to show you exactly how seamless this experience for clinician. Let us take a look at a brief 30-second demonstration of our VerEIT ICU dashboard in action. Okay, this is for the normal patient, and then okay, this is for the normal patient, and then for the patient with the tumor, you can see in this one. This one. So this is anatomical mesh, and this is the lifetime monitoring, as you can see in my screen. And then for the AVI and health standard AI, for the health standard, we use the FHIR for clinical contact retrieval and DICOM web for secure box integration. Furthermore, to protect patient privacy, we employ a federated learning model. This means we only send encrypted AI model wakes to the cloud, not protect health information ever leaves the hospital boundary. And then we are VerEIT.AI. We are making lung ventilation visible, actionable, and entirely safe. And thank you for your time, and we welcome any question you may have.
Unique tracking system. What DICOM object type, what subclass did you use to store the conductivity maps?
I use the DICOM web to store data because the data on the node edge will be on the NumPy array. So DICOM web is standardized data transfer, right, from the other device to other from the one node to another node.
And so DICOM web to do the actual transfer of the data object. The CT scans would be performed using a DICOM CT image type. The conductivity maps, which flavor of DICOM object was carried over the DICOM web?
Yes.
Okay, and for the sensitivity of the tracking, how small of a nodule are you able to monitor?
Do you mean the small, how small the conductivity that we can track, like?
So what size of a tumor, maybe by diameter?
Oh, by diameter. I think by the diameter we can track to until maybe around a centimeter. I mean 1 until 3 centimeter we can detect it because it's a large number. But when the tumor is so small, maybe under 1 centimeter, maybe millimeter, it's hard enough to detect by using electrical impedance tomography. So that's why we need the CT scan baseline for the initial phase. And then for the monitoring, you can use the AIT.
Sure, very cool.
Great job, VerEIT.AI. Thank you so much, and thank you for being willing to demonstrate over the internet, because I know it's different and it's a little bit harder when you can't see the feedback. But thank you so much for joining us. Next up, we have the team number 6, and team number 6 is Open Imaging Data Model, OIDM.
Morning, everybody. My name is Michael Hood. I am one of 2 team members that worked on this project from the OIDM, the Open Imaging Data Model, myself and Dr. Tarik Alkasab. I'm excited to show you our project today. First thing is we have a website. So if you'd like to go ahead and open this up on your phone, this is a navigatable website, and I'm going to go through what this is here in a second. So I'll leave this up for a moment. So to start, radiology has a memory and context problem. You know, every part of the chart, you know, think about a lab like potassium. You can trend it over time. Hemoglobin, you can trend it over time. And AI is capable of reasoning over this structure. However, in imaging, that's not the case. Let me go ahead and advance my slide here. You know, if you asked, trend this pulmonary nodule for me, you cannot do that. I mean, we look here on the right, and you know, you have different pieces of text stated by 5 different people. You know, you have a 5 millimeter nodule. On this study, it's stable, and the next one, it's unchanged or similar to prior. There's different language about describing the same entity in the patient. And the problem is, we hand these to AI in the same way that we would hand these reports to a human. We ask the AI to essentially filter through the entire report every time we want to reason about certain findings. You can see here that this is the example of a AAA, which is, as I was saying, you know, every report is describing it differently, and yet it's the same entity in the patient. And so our goal is to transform the siloed narrative text of radiology reports into structured data that then can be aggregated over time and then reasoned against, tagged with the correct ontological codes, like anatomy, like RADLEX, SNOMED, et cetera. What does that look like? And I'll get to the demo here in a moment, but I wanted you guys to be able to play with it as I talk. What we're doing here is a one-to-one translation of the radiology report into structured data. So you can see on the left here is an example of a radiology report, and then on the right is what a simplified version of what the extraction of that might look like. And again, you are aggregating these across exams, across time to create an entire personalized package of data about the patient, anything that imaging has ever said about them. So once you have the structured entity that's been extracted, here in this case a pulmonary nodule, you would then tag it with the ontological code of an anatomic region. So we have an anatomic locations section of RADLEX that we've implemented, and it essentially allows for anatomical roll-up. You know, if you have a lung nodule and it's stated that this is in the right upper lobe, that location is tagged definitively. And so I'll show you here in a moment what that enables. The overall structure of kind of how we think about these reports is this. We have the initial radiology report that has just plain text. Then after you perform a structured extraction on those, you want to basically get all of the findings out of it, a one-to-one rip, and then you get what's called an exam finding list. If you aggregate those exam finding lists across over time of multiple patients, multiple exams for a patient, you can get that patient's so-called imaging problem list. And again, what we are answering to is the need for like the clinical problem list or other labs. You know, we want to harness all of the rich data that exists within radiology reports and use it just as we would any other lab. And here are some of the downstream applications that are enabled by something like this. So let me show you the IPL viewer that we've coded. And so you may have to squint closely, but this is a person here on the left. And what this represents is all of the data that one patient's entire imaging history, and again, organized by where the findings are in the body instead of by which report they come from. And so let's take a look at one of these, for example. If I click on pneumonia, I can see that on this chest X-ray, the patient had pneumonia. I can see the source text provenance that brought this finding forward, and you can see all of the individual findings are tagged with metadata, right? So we can say that this was seen on an X-ray, on a CT. We can see what like body region this is part of, which subspecialists might care about something like this, how many times we've seen this finding, and so on. You know, eventually we would want to enrich this with even more foundational context, essentially. How long would we expect this thing to last? Is this a neoplastic finding, an infectious finding, et cetera? And as you click around, let me move this. You can see findings that are current, like something that is a problem right now, versus something that is always intended to be there, something like a calcification or an old fracture that's healed. And so start to be thinking about what this could enable if the data is structured in this way. It powers a whole lot of downstream applications. One off the top of my head that I've been chasing hard is efficiency tools. As an emergency radiologist, we are swarmed with studies and trying to develop tools that will improve our ability to read those exams faster. So for example, if you knew that a bunch of the imaging findings were old and we're always going to be there, then I don't have to spend half of my time redictating old things. I can just pull them forward with a single button click. Let me show you another piece. So you can see how everything is organized by now anatomic regions. We have thoracic findings. We have then within the thorax, the subregions. So we have chest wall, heart and pericardium, lungs and pleura. And we can look in the pelvis. We can look in the abdomen and see like a hepatic cyst. And so we've cobbled this together in the last 3 days. So this is a rough demo, but this is a proof of concept to show what this can look like. And so let me kind of zoom out again. What this is, step back from the interface. This is a compact, pre-compiled summary of everything imaging has ever said about this patient. And so why is that important? There's three things. First off, systems that are working off of radiology reports, it's expensive to chug these. If you're pulling findings out of dozens of reports, recognizing the same findings over years, this is pre-compiled and it happens up front. And so because it's structured and pre-compiled, you can filter it to whatever it might be needed at that time. You don't have to look through the entire report if a breast imager only cares about certain findings in the chest, or if a urologist only wants to know about the kidneys. It allows them to quickly get into that context of the patient's data without having to look through everything else. Finally, because it's anatomically grounded, everything is anchored to an anatomic code, and that carries like what that location implies clinically, right? It could enable downstream clinical reasoning. And so that's what this is in a sense. It's a grounded context for reasoning over a patient's imaging for AI systems to be reading along them. Let me move to my last slide. And so to kind of sum it up, what this represents, the imaging problem list, structured, aggregated, longitudinal history of every finding that a patient's ever been seen in their reports. And it becomes then anatomically grounded context for AI. And this is the future forward. We used FHIR standards, RADLEX anatomic locations, and a developing IHE imaging problem list standard. Thank you very much. I'll take questions.
So I think this is really fascinating. It's an interesting area of research and a great presentation. And clearly, the UI is something that is fairly intuitive. So compliments.
Thank you.
One of the things that I'm concerned about is the idea that the problem list is the two things. One is that it becomes the Hotel California of put something on the problem list, and then you never are able to take it off. And I recognize that you have some temporality of like how long the findings are expected to be there and so on and so forth. So my question is, how do you think about taking things off of the problem list, number one? And then number two, how can you distinguish between an error that was made in taking it off and actual truth in changing the state of the patient?
This is a big part of the debate. And yeah, Howard, we talked about this at another session. So I think the first part of it is saying that we're not creating anything new. These are all direct one-to-one translations of what radiologists have already said in reports. And then the aggregation of those things over time, sort of the disambiguation, that will become an additional logic layer that we will have to develop. But I agree that there are many instances in which, like if you have an addendum to an exam that changes the nature of a finding, or if you have even implicit disagreement between radiologists across exams, that happens a lot. And so I think what it would be is once we have like sort of developed this more concretely, for real patients and deploy it, you will start to see ways that we can develop logic to say, okay, if let's say this finding has been stated by X amount of radiologists and one person says otherwise, then perhaps that would be a way to say like maybe this person's wrong. And so it's an open development. I agree, it's a very hard problem though. What I do think though is that it has to be opinionated in some way. It can't be just an open standard for people to just see what happens. Like we have to guide the field forward, and especially as radiologists, I think that in a world where AI is making findings for us, is drafting findings for us, that we become stewards of those imaging findings. And as our role shifts, I think some of this will become more clear. Excellent. Thank you, guys. Oh, what's that?
Thank you. My voice just went silent. Thank you, Open Imaging Data Model. Next up, we have one more, the team number 7. We have Hook, Line, and Fire, a CDS Hooks framework for automated radiology follow-up and reporting.
All right. Hello, everyone. We are Team Hook, Line, and Fire. My name is Sam, and I'm joined here on stage by my team members and first-time hackathon participants, Eric, Julianne, and Grace. So we were working on for the last 3 days developing a CDS hooks framework for automated radiology follow-up and reporting. So to start off, we kind of want to dive into our problem a little bit. And the first piece of that is the fact that radiological reports lack a standardized structure. So these are usually generated and sent in a free format text format, so usually as a PDF, with few, if any, codes embedded in them. So another problem with this is the inconsistency in tracking follow-up requests in these reports. So there's many different ways to describe the same radiological finding in a report, and it's up to the discretion of the clinicians to, figure out what these variations may mean. And then also sometimes initial observations and incidental findings can be overlooked. So the combination of these two issues can result in patients showing up with more severe issues that were initially reported in the first report. So there's a couple of different aspects of the post-reporting workflow that are affected by these problems. So the first of these being clinical practices. So that includes follow-up diagnosis and care, image quality, and care team communication. We also are affected by the administrative and quality processes, such as case reporting to the FDA. Outcomes research can also be affected by these problems using the radiologist outcomes and observational research databases. And then finally, there's a public health application as well, just in terms of healthcare system quality improvement.
So to understand our project a little better, we are going to take Sharon. Sharon is a 70-year-old woman who was diagnosed with Alzheimer's back in 2025. As a result, she was prescribed lecanemab to help mitigate the cognitive effects. She also goes to the visit for follow-ups on a regular basis, during one of which she had an MRI where they discovered hemorrhaging. So the radiologist is going to fill out the report, and once it's finalized for our system architecture, it's going to activate the CDS hooks, and then there's going to be a domino effect. And once all the dominoes have fallen into place, the bundled reports are going to be sent to the FDA.
So just to take a look here, we did a mock-up, just a user interface of what the reporting would look like for the radiologist. So an important thing to note here is the sign button in the top left corner. So that button is crucial to triggering our back-end pipeline.
So how do all these triggers happen? We are using CDS hooks. So to kind of give a brief description to start, some workflow event is going to trigger that CDS hook. In this case, it's when the radiologist is signing that radiology report. So then the CDS hook will trigger the external backend pipeline and will send over some context like the report ID and the patient ID. Then some actions will occur through the backend pipeline and may be sent back to the EHR. So as part of this project, we have drafted 4 different CDS hooks proposals and received a lot of feedback from the HL7 CDS working group, as well as technical professionals from Jacobian reporting, as well as RAD.AI reporting. So the 4 proposals that we have can be generalized to not just radiology reports, but any specialty report. So the first one is report create. So this one would trigger when a provider opens up a new diagnostic report. So an example could be it would select the correct report template. And the next one would be report assist. So this one would be if the provider wanted to request assistance from an external interoperable CDS. So an example would be automating the lung RAD score calculation to be submitted to the lung cancer clinical screening registry. Next would be report review. So if the provider is finished with the contents of the diagnostic report and wants a review of something before they sign it and finalize it. So an example would be using an LLM to fill in the impressions category of the radiology report after the radiologist has filled in the rest of the report. Moving on, for our last one, we have report sign. So that one is what we are demonstrating in our example demo here. This one would trigger when a physician has signed a diagnostic report. So an example for this one would be to search for different codes within the report, and then it could automate different patient follow-ups. Moving on.
All right, guys, time for the demo. So, for the demo, here we go. So over here, you can kind of just see our lovely lady Sharon. It's going over about her having lecanemab as a medication as well as her hemorrhage. Then you have your MRI report that's being filled out by a radiologist. Once they're saying it's all good, they sign, and that triggers our backend. So that's then going to go through a couple steps, eventually ending up sending it to the Happy server, which would be acting as the FDA server in the real world. So now that we've seen the demo, let's dive into some of the actual beats. So system architecture. So for the system architecture, there's a couple different parts to this. So as we said earlier, it starts off with the interaction with the UI, but then that triggers a CDS hook. And then from the triggering of the CDS hook, what we're going to do is we're going to pull the report ID and patient ID in order to get the information that we need to start doing an automated process of pulling the LOINC code for hemorrhages. If that person does have a hemorrhage, then it's going to then send a further query about the medications. And if lecanemab is one of the medications, then that triggers a further query finally to what would be the FDA server, sending on a FHIR message saying, hey, this person was someone that had a hemorrhage with lecanemab.
So it's important to note here that the project that we did focused on only one of the possible use cases that we mentioned previously. So in future directions, we would like to focus on the other three categories. So the first being clinical practices. As the last presentation mentioned, and we dove into a little bit in our project last year, an imaging problem list is something that could be applicable here. So that would allow us to have structured notes put in for future radiologists to look at, just kind of improving outcomes and workflow. We also could look at outcomes research in OMOP, and then finally the public health application, specifically looking at the example of clinical registry submissions and maybe looking at screenings across areas, patient, sex, race, and other categories. This is also a good point to mention that for our project, we did use generative AI just to help us with the user interface design and some of the back-end coding.
We would like to extend additional gratitudes to those who have helped us throughout the entire process. And then we would also like to thank you for your time and attention today. If you scan the QR code, there's our contact information for the team. Does anyone have any questions?
First, I'll start with what's probably a quick one. We're pulling 4 different FHIR resources for medication. Can you talk to your choice to pick all 4 of them rather than say focus on administration or dispense or something?
Yes. So at least for the medicational standpoint, with how we structured it, the idea was to check all medications and then check against the LOINC codes, just in case there is something specific that is not necessarily included in administration or something along those lines. But generally, the idea is just to see everything that's out there, just in case some other part of the back end is just not coming along. Yeah.
Thanks. This is a really exciting presentation. I think one of my current existential crises is trying to think about how we would manage all of this decision support information in a bunch of different places. And I think that one of the things that seems implicit here is that CDS hooks is a place that an institution could really institutionalize the decision support pieces, and then still be able to integrate that at the point of care into a bunch of different applications. And so my question, sorry, that was a comment. The question that I have for you is CDS hooks something that you could integrate with Firecast so that from an application perspective, I could actually ask for and retrieve those CDS hooks in real time?
Yes, it would be able to be integrated with Firecast. We obviously weren't able to do that within the scope of these few days, but it would be something that we could look into in the future.
Thank you.
Well, since there's a couple moments, so I really like the hooks that you're proposing for the reporting part of the process. Those four seem really sensible. Have you looked at some proposals? We need more hooks. Have you looked at some of the proposals for things leading into the acquisition process, or looking at the referring physician's interaction with the report?
So we haven't looked into pretty much anything besides for when the report is generated to when the report is finalized and signed. But we are open to suggestions, and obviously there is a need for more CDS hooks as the list is very slim.
Great job, team Hook, Line, and Fire. Okay, next up we have our next online presentation, and that's going to be Social Determinants of Care Continuity, or SDOH Care Continuity. That's right. Anytime that you guys are ready, you can go ahead and share your screen and get started.
Good day, guys. I'd just like to find out if you can hear me. Can you see the screen?
We can hear you and see the screen.
All right. Thank you. I'd just like to give out a big gratitude for this opportunity, of course, to the SIIM leadership and the tribe, especially our team here from Impageni Radiology that made this possible, and my wife, of course, Julianne. So the problem is, of course, if we look at patients specifically, if they go for any form of radio scans or medication, or even their reports, these discrepancies, they don't understand it. There's really a big disconnect between patients that doesn't know themselves. They don't know what's exactly wrong. They don't know how important it is and why they do need to take medication or stuff like that. There is a few things that you realize in the medical industry. You see some healthy people that die early, and the exact opposite is also true, that some people just survive against all odds. So how we did it, our team did it, is with a 4-agent orchestration. But while I'm explaining you about the 4-agent orchestration, I'll rather just show you. First, we've got the Forge agent. Hopefully you can listen to what it's telling you. You can read it as well. It's not okay. So just to make it easy for patients to receive their own images, not just their own images, but their reports, their medical scripts, in everything that's medically related to them, and easy for them to share it as well, but share it in a way that's relevant. It doesn't help you share images from decades ago with with a referring doctor or a doctor's visit. So that's much harder than anticipated. The last 2 agents, especially from the SDOH navigator, and especially the PACS continuity agent, the last 2 agents is based on the OpenClaw framework. If I can just show you an example here. Just a moment for me. Say, for instance, I want to ask about the SIIM patients. It's deterministic, but if it doesn't know the answers, then it falls back to local Gemma. So there's no API calls. It's mainly built for offline use. show me the list of SIIM patients. Okay, and then I can go a little bit deeper. So it tells me a little bit more perhaps. Show me some Jessica. Okay, you can see how I screwed it up. Body part identity, and there's some fields missing here. Say for instance, show no. Some patients it's supposed to get right. Yeah, you can see it's right. Okay, but same with. So I'm just going to play a video as well, and then I'll open up for questions. All right, I think I've sorry for that. All right, and yes, I'm open for any questions. Can you hear me?
So I got the impression in there was the idea of sharing the patient's imaging records, and so but I couldn't quite follow. Let's say the patient's been scanned at an imaging center, their images are available on the PACS there. What were the image transfers you would be talking about after that? Where would the image go? What protocol?
Okay, so this is a great question, and thank you for that. This is especially why the SDOH of the social determinants of health agent is connected via OpenClaw now, of course, to different platforms, not just WhatsApp, but you can even connect it to emails and stuff like that. So if a patient requests his image, the agent doesn't send it automatically. It's human in the loop, so it notifies me or as the IT person, hey, listen here, this patient is requesting his images. Not like he's supposed to request it at all, but then it makes it a lot easier for me to share it with the patient. So just to share that PACS link or to share that OneDrive link or Google link with the patient, with his PACS images or with his report. And it's much easier for that patient as well, especially if it comes to, say, for instance, the medical scripts or the referring letters or the reports for the procedures that is done, just to condense that in something that's relevant to share with the next visit and to translate it for a patient. Because most of the patients, if you can think about it, if the doctor speaks to a patient, there's either a language barrier. Okay, I'm from South Africa. Here in Africa, we've got a lot of different languages as well. We're kind of diverse. So just to bridge that communication barrier, it's not just language, but frame of reference, social circumstances, stuff like that. Hopefully it answers your question.
Okay, so yeah, there's another question, I think.
Sure. Thank you. I think both social determinants of health and continuity of care are important topics that are often under-discussed in AI. But particularly because this is about social and things are language barriers and gender, racial bias comes into play. What work have you put into the system to assess for possible biases in the multi-agent framework? And how do you know that it's not, let's say, preferentially being more, the results are not more accurate for one particular subgroup compared to a different subgroup?
Great question. And just to make something 100% clear, none of the agents gives at all medical advice. So what the agents only does is translate what it's given to it or index what it's given to it for the patient in the frame of reference that the patient can understand it. And this is why the 4 agents work on different levels as well, just to understand, to empower the patient to understand himself better. In the world of recovery, just to explain it, if you don't know yourself, if the patient don't know much about himself and his problems of his illness, then the path to recovery becomes a lot more difficult. Does it answer your question?
Thank you. Yes.
Thank you so much. That was Team Social Determinants of Healthcare Continuity, and thank you for being online because we know that's a little bit harder, and we appreciate you, both you and VerEIT.AI, doing your presentations online. Okay, next up we have team number 9, Echo Sherlock.
Good morning, everyone. It's our pleasure to be here today. We're Team Sherlock, and we'll be talking a little bit today about a solution to a very common clinical problem that we face. So what is heart failure? Heart failure is the inability of the heart to pump enough oxygenated blood to the rest of the body. As a practicing cardiologist, I can say that one form of heart failure called heart failure with preserved ejection fraction is particularly challenging to diagnose. And why is that? It's because the clinician is expected to integrate clinical data that includes the information that's in the labs, that's in the clinical notes. They're expected to review the imaging and understand and be able to interpret it, as well as put it together with the patient in front of you and make an understanding of it. Now, there are some established scores like the HFpEF score that can help the cardiologist figure out if the patient has heart failure or not, but these can be tough to implement in a clinical setting. For example, let's say we have a 59-year-old woman who comes in, she's feeling short of breath, she's been that way for the last year, she gets an echocardiogram or an ultrasound of the heart, which shows that her heart pumps fine, yet the patient still feels really poorly. The clinician understands that there's something going on, but they don't quite know what the diagnosis is. So I'm going to show a demo of our product, which is Echo Sherlock. This is winter EHR. As many of you know, we open up the chart of a patient in winter, and we would have a clinical decision support tool with a card that would pop up. This card would provide a likelihood of HFpEF. So in this example, this patient has an 80% likelihood of HFpEF, as well as an evidence statement for where that comes from in the EHR. If we move on, we'll notice the things that go into this calculation that's provided. So we're going to need results, so laboratory tests like NT-proBNP, We're going to need encounter documentation in the documentation section, which will provide us with physical exam findings as well as symptoms. So this is all going to be unstructured data that will get pulled out with an LLM, and then we'll come back to how that gets integrated later in a multimodal fusion way. And then most importantly, the imaging. So in our demo example, we'll be using the raw imaging data, the DICOM imaging. So this is an echocardiogram that's moving through really quickly here. This image shows how well the heart pumps. So this is one of the video images that will be integrated. These images show how well the heart relaxes. All of these are key for making a heart failure diagnosis. And then lastly, as an example, this is a patient who had less likelihood of HFpEF. So if you open this patient's chart, the CDS card shows that the HFpEF likelihood is only 7%. So I'm going to turn it over now to Dr. Jen Park, who's going to go into how exactly this works.
Thank you. So what's going on in here? So we just saw the mock EHR, which is a simulated EHR that you saw. And then we're using HL7 FHIR, CDS hooks, and DICOM files. So instead of having clinicians go hunt down all these variables, our product is looking at the images, notes, and clinical data and process it through individual AI systems and then integrate it into a fusion model to give an exact probability of whether this patient would have this specific type of heart failure. Okay, thanks. For the imaging AI models, we adopted the open source model called Echo Prime. So this is a multi-frame informed vision language model and comprehensive for the echocardiogram interpretation. And as you can see on the right side, that's the result that we're seeing. It's pretty good at capturing or classifying whether this patient has this condition or not. And then for the notes and clinical data, we use the GPT 5.4 Nano to process the discharge note to get all the structured and clinical information out and use the clinical data that is already structured in EHR and combine that into logistic regression. And finally, adding that with the echocardiogram result back to the late fusion AI system to give the final probability. In terms of the user experience, whenever the doctor is opening up the patient chart, CDS hook is called and finalize all this integrated data into the models. And it will give pop-up show on the right side, clinical decision support, whether this patient has this condition or not with a probability and also the evidence. So you can see the evidence is showing in the text. As you can see, the clinician doesn't have to just believe the model, but you can read about like how this model has come about this solution.
Okay, and like many of the folks here, we did get help from our good friend Claude. We use generative AI for some of the code assistance and for, as was shown just now, the extraction of information through the LM call in GPT. We did our best due diligence to be learning this on our own and to be implementing on our own. So much of the code is written by us and tested by us. For next steps, there are established risk scores for HFpEF. There's the HF2PEF score, and we want to benchmark it against those to see how we calibrated our risk model against those. It would be useful to validate this across larger multi-institutional cohorts, so using multiple different sites and integrating those data to see how generalizable this late fusion model is. And then finally, we would want to see as an evaluation or implementation framework how this would actually impact and be used within a real clinical workflow. We would be remiss without acknowledging some of those who helped us. So Dr. Blake Dewey, Dr. Paul Nagy, and of course, Teri. And we did get help from some of the services that were used here with Winter and then Mimic 4, and then of course, SIIM. And we'd like to thank you all for listening. And here's a picture of my dog. So this is really exciting. I could see a lot of applications of a similar technique to other problems where you're using a similar pipeline. So I wonder if there's some value in talking about some of the challenges that you ran into in the implementation process and trying to, glue these things together, which is kind of a classic informatics challenge.
Yeah, one of the challenges that we faced is that running the imaging algorithm, especially the video frame, takes a long time. So it would be very difficult if the CDS hook kind of triggers that. So we thought that probably that portion should be in PACS, or whenever the echocardiogram is finished, then the background algorithm should run so that only the fusion model will take the result out of it. I think that will cut down a lot of the loading time for the patients. For implementation, it depends on each institution's having different workflow to go through this diagnosis. So we would need to customize based on the individual workflows.
And I guess, so it looked like for the extraction from the existing record, all that was based around, NLP type processing. Did you take a look at, for example, what it might look like if you had FHIR observations and FHIR elements from the records, or is that more future work?
So the resources themselves, so if Winter as like an EHR, the entire thing is built on top of FHIR. So all of the records are retrieved through FHIR, that being like the document references, the nodes, the labs. And so everything's being processed through it, and then that gets piped through the LLM. That's what you're asking.
Well, I was actually thinking, so rather than a document reference, that if some of those documents were in fact already FHIR coded, and if there were then particular observation codes you could go looking for as a more direct cut to the input values.
I think that's a great point. It'd be really helpful for the things that are FHIR coded, but certain things like physical exam are not reliably FHIR coded or at all. And for something like heart failure, which is ultimately a clinical diagnosis, you really do need to have that.
Thank you.
Thank you, Team Echo Sherlock. So next up, we have team number 10, our last presentation for the morning. And this presentation will be on RADGuide, a pre-order imaging copilot for non-radiologists.
Hello, my name is Cindy and I am a traveling CT technologist, and I am going to go over the problem. Okay.
Hi, everyone. Thanks so much for hanging around. We're incredibly excited to present to you our project, RADGuide, a pre-order radiology co-pilot for referring clinicians. And RADGuide aims to address several fundamental issues that stem from this notion or reality that arguably the most consequential moment in radiology happens actually before the scan takes place. And it's in this pre-order, pre-scan period where we see several issues that arise related to clinical deficiencies and operational deficiencies. It's well known that poor referrals result in reduced diagnostic accuracy. And it's estimated that between 20 to 50% of emergency scans are inappropriately ordered. And this has resulted in approximately $12 billion of erroneous spending in the US alone each year. And one fundamental reason for this is that referring clinicians are not radiologists, and they range in clinical specialty and experience from specialists and attendings all the way to interns and residents who are responsible for most of the inpatient ordering in hospitals.
Okay, so I'm Cindy. I'm a CT technologist and I travel across the country to different hospitals, and we have a problem with order protocols. The physician will put in the order gets reviewed by either myself, a technologist, or a radiologist. It creates a disruption in our workflow. It delays patient care. So for example, we get an outpatient, they come to us, and the reason is not matching, the clinical indication is not matching the order correctly. So we have to contact the provider. Sometimes it's very hard to get in contact with that provider to get another script sent to us. And that creates kind of like a delay for the patients and the cost. And so basically we came with this diagram here. There's a high resolution, for example, high resolution CT chest that's ordered, but that can also be ordered as a low dose CT chest. It saves the patient radiation. It also gives them the radiologist the same information that they're looking for. So it does create a problem there. So I'm gonna turn it over to.
So the clinical challenges that are currently being faced is that sometimes there are orders for the wrong examination, and there's sometimes duplicate studies being created that can increase radiation dosage. Additionally, sometimes indications lack clinical context that can hurt the radiologist's interpretation of the scan. This causes many poor outcomes, such as additional radiation, delayed treatment, more financial costs for the patients, as well as unnecessary operations. Thus, the goal of this project was to use a RAG model to improve GPT-5's recommendation for assisting referring providers for the next best imaging exam. We used the American Colleges of Radiology's appropriateness criteria, which are the gold standard for understanding the next imaging test. We also go through the patient's medical history using FHIR, as well as their imaging history using DICOM Web. The second goal is to assist referring providers on writing well-written indications that can help the radiologist in interpreting scans. Additionally, we can caution referring physicians against making repeated imaging scans, and we also propose CDS hook with order assist, which fires when RADGuide is being called.
So just a brief overview of the ACR's appropriateness use criteria. So it essentially is a composite of several gold standard recommendations for what should be ordered for a specific clinical indication. So there's thousands of clinical variants. It encompasses all common radiology modalities and body regions. So we were able to basically acquire this from the ACR's website and use this as a knowledge base for our system. So essentially, as you can see here, depending on the indication, a specific procedure or scan type is graded on a scale from 1 to 9. And essentially, depending on basically expert consensus amongst radiologists over the past 30 or so years, we've come up with these criteria that are well validated, and this is what we're using to inform our system. And you can actually see the appropriate use criteria yourself at this link here.
I'm going to be brief on this because I want us to spend a little bit more time on the demo, but essentially everything rides on the standards here. We pull the patient over FHIR, we bridge over DICOM Web by the study UID, and speak CDS hooks back out. We even wrote a CDS hooks proposal for the gap we found in the standard. On top of those rails, AI does what it does best: semantic search across 1,227 ACR scenarios, driven by the indication and drafting better conditions that the clinician approves. but the floor is deterministic. Safety rules, a clinician validated, thorough testing, zero network dependencies. So the guidance is explainable. The demo can't die on our conference Wi-Fi.
And I'll also be quick here for time's sake, but we are using a multi-agent framework for this. So it takes the initial order from the provider and identifies the ACR scenario that most appropriately applies, and then uses a looped system to continue generating questions to kind of prompt that clinician for more information. And we can get started with the demo.
All right, so this is a QR code to the website where we're hosting the demo. If you want, you can use it. So okay. Basically, we're going to be using Ravi here, which is part of the SIMS's data set. And let's say Ravi is coming in for a scheduled outpatient appointment, and he's complaining about a headache, symptoms of like abscess. So I'm going to order a CT head with contrast, and I'm going to say headache, rule out infection. And I click on submit order, and I can also see the summary of the patient. This is being pulled from like FHIR and DICOM web. And when I click submit order, you can see that the AI model actually corrects me and tells me to do an MRI head without and with contrast, because that's a better test to be using than a CT head with contrast, because MRI is better for ruling out infection. Additionally, it asked me further questions like, what is the characteristic of the headache? Is there a history of head trauma? And then it also cites to me the appropriateness criteria it's using to give me the recommendation. So here you can see it's using variant 7 of one of its documents, and it's citing this one because Ravi's 85 years old, and and he's like older age. Additionally, if we say, is there a history of head trauma during the appointment, and Ravi tells me, oh, I had a fall like a few days ago, I can type in unwitnessed fall. I can say apply answers and reanalyze. And RADGuide will now look and will tell me to do a CT head without contrast, because that's a better imaging exam to check for bleeds, as well as like fractures and etc. So this is basically the demo is useful for identifying the best imaging criteria, as well as telling me to giving me like better indications and like helping me reanalyze the indication as well.
One question. Thank you very much. Great presentation. I think it's an important clinical problem. One of the questions that I had for you was whether you considered using things like ICD to try to extract that from the appropriateness criteria. It looks like that's completely absent from the appropriateness criteria. And then that's also a really important part of the order that's required, because that's what we're going to use for downstream billing purposes. So just a question about using ICD as an additional ontology and standard.
Yeah, so we could definitely like incorporate ICD into this problem. What we're doing right now is that we took the ACR criteria, we passed it into an embedding model that creates vectors, and then we also get the clinical indications, makes it into a vector, and does similarity search on that. So it is like kind of looking for like semantic similarity and things, but we could definitely also look at an ICD-10 lens approach. So.
We just want to thank you guys. Special shout outs to Les Folio, Mohannad Hussain, Tom O'Sullivan, Alex Barrington, and the SIIM Philanthropy Committee for their assistance on our project. And last disclosures that we do is Google Anti-Gravity, OpenAI, ChatGPT, FO Mini, and Claude Fable 5 in our project. Thank you very much once again.
Okay, and that wraps up the presentation portion of the SIIM Hackathon. We would like to thank all of you for being here. We would like to thank all of the teams who have put in a lot of time. I see a lot of tired eyes in the audience here. I would like to thank the people who participated online, as well as people who participated in person. Please vote. I noticed several cell phones out already. Please vote for the Audience Choice Award, because you have a say in who's going to walk up on the stage later. I would like to one more time thank SIIM Fund. We have quite a few vendors as well as individual donors, and without them, we would not be able to have some of the participants here. To that And we had 5 people up here. We had Michael, Caleb, Nick, Yash, and Julianne, who were here as part of the SIIM Fund Travel Awards. And so you would not have had the participation in the hackathon presentations that you did without SIIM Fund. Right, Mark? And chickens. Yep, go chickens. And last but not least, 2 last reminders. Right after this, immediately following this, over in the hackathon area over here, there's ice cream. So please come and visit and get some snacks. And then finally, the awards will be given out as part of the Dwyer lecture later this afternoon. Thank you so much for participation.